Hello and welcome to this movie about rectangular waveguides. In this movie, which is part 6 of the series, we'll learn how to use the equations that we've derived to calculate the different quantities that describe the waveguide and the electromagnetic wave that propagates through it. Here is an example of such a question. We're given the dimensions of the waveguide, its width and height, the frequency of the wave that propagates inside it, and the type of mode that it uses to propagate with. We can get the values of m and n from the mode type, which we need to know so as to plug them into the equation. We can also convert the dimensions of the waveguide into meters. We'll firstly find the cutoff frequency for this mode and define the variable that we'll use for it. This is the equation that we'll use to find the cutoff frequency from what we are given. Substituting the variables into it gives us this, and evaluating this expression gives us this answer. Now we'll define the variable for the cutoff radial frequency. We can use this much simpler formula to find it, since we've just calculated the cutoff frequency. Substituting the values into it gives us this expression, and evaluating the expression gives us the cutoff radial frequency. Scientists and engineers like this quantity because it is easier to work with when they use sine and cosine functions. Now to find the propagation constant, which is a measure of how the wave propagates in the waveguide. It is its wave number. It can also be equal to kz and gamma. This is the equation that we'll use to find it. Since beta represents a propagation constant with a purely imaginary value, the formula under the square root sign is set opposite to that set to find gamma. We get this messy looking expression after we substitute all of the variables into it. It's very easy to program a computer to solve it for you. And so this is what the propagation constant is. Now it's a good idea to evaluate this expression because we'll need to substitute it into the next few equations. Substituting the numbers into it gives us this expression, which evaluates to this dimensionless number. So now to find the wavelength of the wave in the waveguide, we'll use this formula to find it. Plugging the numbers into it gives us this expression, which gives us this wavelength in meters. We can use this constant to find the propagation constant using another formula. And this is what this formula is. Plugging the numbers into it gives us this expression. This is what the propagation constant is using this equation, so we can find it a second way so as to check it, and it is equal to the first calculation of it. And we can use another equation to check that these quantities are correct. This equation is correct if these quantities have been found correctly. And substituting these numbers into it shows us that these numbers are correct. Now to find the two different sorts of velocity, we'll find the phase velocity first, which is the apparent velocity of the wave in the guide. It is impossible to actually see it, but you could imagine what this wave looks like as it flows through the guide. This quantity is usually faster than light. This is the formula for this velocity. Then we'll plug the values in, and then we'll get this value for the phase velocity, which is faster than light. It isn't the speed of the signal or the actual energy of the wave, so it doesn't violate any laws of the universe in being faster than light. So now to find the group velocity, which is the velocity of the energy of the wave. This is the formula that we'll be using to find it. Then we'll plug all of the values into it. And so we get this value for this velocity of the energy of the wave, which is less than that of light. It is slowed down by the propagation through the waveguide. Now to find the wave impedance of this waveguide for the TE mode. This is the formula that we'll use to find it. Then we'll plug all of the numbers into it. Eta naught is the wave impedance of free space and is equal to this amount. So this is the wave impedance of the waveguide for this particular mode. Now to find the wave impedance of this waveguide for all of the same values of N and M, but for the TM mode. This is the formula that we'll be using, which is different to that for the TE mode. We'll plug all of the numbers into it like we did before. And so we'll get this value for the wave impedance in this case. Now to try an exercise where we have to work backwards to find the value of the longest width of the waveguide, which will give us a particular cutoff frequency for the fundamental mode. A is always longer than B by convention, so we'll have to find A. This is the equation which relates the cutoff frequency of the fundamental mode to the longest width A, which is a designing problem. Manipulating this equation gives us A as the subject of this equation. Plugging the numbers into this formula gives us this expression, which will give us this answer to A in meters. And this answer can be written in centimeters. Waveguides usually have the value of A in this range. Here's another question asking us to find the value of A, this time from some other variables. One is the frequency of the wave guided by this waveguide, and the other is its propagation constant. This is the equation for the propagation constant, which is beta, so it is propagating as a wave and not undergoing exponential decay. This is the cutoff frequency for the fundamental mode. We've already seen this equation in the last question. So we'll manipulate the first equation, which gives us another equation for beta. We'll substitute the second equation into this one. Now we have an equation containing all of the variables we've been given and are trying to find, and eliminating the cutoff frequency, which we don't know and are better off ignoring in this question. We have to manipulate this equation to make A into the subject of it. So here A squared is the subject of this equation. Square rooting both sides gives us the equation we need, which is A as a function of beta and F, and all the other terms are constants, and the number 4. Now we can plug all of the numbers into this equation, which gives us this solution for A in meters, and A can be expressed in centimeters. I used all of the algebra to find this messy value of beta, so I could get this neat value of A when I used the algebra to find it. You can have fun making all sorts of computer programs to find different quantities found in the waveguide, so as to get used to using the algebra. This is the last video in this series, and I hope that you have learnt a lot from this course of 6 videos, and enjoyed it in the process. Please click on like and subscribe if you'd like to see more of these videos, and leave your thoughts and opinions in the comments.